Alright, we're going to finish up this section by looking at formula and molecular weight. And these are the sum of the atomic masses of the atom in the chemical formula. Last year, you may have heard this referred to as molar mass. Here we're talking about the same exact calculation. So we're looking at these atoms on the periodic table at their atomic masses, and we're going to add them together and get the sum if we have a compound. This can also be referred to as formula weight or molecular weight, and those are calculated the exact same way, just looking on the periodic table and adding those values. But the key there is just in understanding the vocabulary. So if we're talking about formula weight, we're talking about the basic unit in a network solid, which to note is usually ionic. So formula weight is usually used if we're talking about an ionic compound, whereas molecular weight is usually used when we're talking about molecules which are covalent compounds. Calculated the exact same way, but make sure you understand the difference in the types of compounds we're talking about. Formula weight, ionic; molecular weight, usually covalent. For example, we could calculate the formula weight for magnesium hydroxide. Formula weight is the term used here because this is an ionic compound. So magnesium, there's one of those. So we do 1 times its average atomic mass from the periodic table. This 2 outside the parentheses is distributed. So 2 oxygens, 2 times 16, its molar mass or molecular weight from the periodic table. And then hydrogen times 2 as well. And then add them together and we see it's 58.33 atomic mass units. This could also be written as 58.33 grams per mole. Mass percent. This is simply the percent by mass of an element in a substance. The percent by mass of an element in a substance. For example, if we wanted to find the mass percent of element fill in the blank, okay, you could say chlorine, it would be the number of atoms of that element in the compound times that element's atomic mass from the periodic table divided by the formula weight or the molecular weight of the compound times 100. So it's the part of the compound that you're concerned with divided by the whole compound. And whenever we talk about percentages, it's going to be the part over the whole times 100. For example, if we're talking about water and we're asked to find the mass percent of hydrogen. In water, there are 2 hydrogens. So that would be 2 times the mass of 1 hydrogen divided by the mass of the entire compound. So we've got our oxygen plus our 2 hydrogens. So it's the hydrogens, 2 of them, times their mass over the whole thing times 100. And we find that the mass percent of hydrogen in this compound is 11.2%. The biggest mistake people make on mass percent is forgetting to multiply by the number of that element in the compound. So a lot of people may have done this problem and found that the percentage was 5.6. But that would be the percent for 1 hydrogen. We need the percent for all the hydrogen in the compound. So 11.2. If we wanted to do the mass percent of oxygen in this compound, there's only 1 oxygen in this compound. So it would be 1 times 16 divided by the mass of the entire compound. 88.79%. When you do mass percent, if you calculate the percentage for each element in the compound and add them together, they should add up to 100. So that's a way to check your work and make sure you're getting reasonable percentages. The second compound that we're going to look at is hydrogen peroxide, which is made up of the exact same elements as water, but in different ratios. So instead of a 2 to 1, like we have in water, here we have a 2 to 2. So I want you to pause and calculate the mass percent of hydrogen in hydrogen peroxide. Okay, hopefully you figured that out. Here's the setup. And the answer, 5.94%. Next up, we want to find the mass percent of oxygen in that compound. So again, if you'll pause, I want you to make sure you can calculate this on your own. Alright, and there's the work and the answer for the oxygen. Again, you could add the hydrogen percent and the oxygen percent together to check your work. Alright, a little bit more history here that goes with those calculations that we just did. This was discovered by John Dalton. If you remember at the beginning, he also added to the law of definite proportions. The law of definite proportions, remember back to the beginning of the section, told us that within a compound, those proportions were always set. So within water, the percent hydrogen and the percent oxygen would not change. But he also came up with this second law, the law of multiple proportions. And that says when two elements form more than one compound, the different masses of element A that combine with a fixed mass of element B can always be expressed as a whole number ratio. Okay, let's try to make sense of that. So two elements form more than one compound. For example, hydrogen and oxygen. They form water, and they also form hydrogen peroxide. Two compounds that have those same elements. The different masses of element A that combine with a fixed mass of element B can always be expressed in a small whole number ratio. For example, in hydrogen peroxide, we have 16 times 2 of our oxygen. And in water, we just have 16 of our oxygen. But both of them have 2 for the mass of the hydrogen. So if we look at the ratio of oxygen to hydrogen in both of these, they're different, right? 16 to 2 in water and 32 to 2 in hydrogen peroxide. If we look at the ratio of these two to one another, we'll see that it equals a whole number. Okay? So the ratio of H2O to H2O2, this ratio to this ratio, equals a small whole number. And that's what the law of multiple proportions says. It says if these elements can make more than one compound, those two compounds, if you compare their ratios, it will equal a whole number. So here they did 32 over 2 divided by 16 over 2. Now how do you divide a fraction by a fraction? You multiply by the reciprocal. So that's what they did here. 32 over 2. This is our ratio from the hydrogen peroxide. Times 2 over 16. This is our ratio from the water flipped because we're trying to divide them. And you'll see it comes out to be a whole number. Okay? So two compounds that are the same compound, they will have the same ratio. Two compounds that are different will have a whole number ratio if you compare them. That's definite and multiple proportions. Okay, here it is again, but we're using our percentages. So they have 88% oxygen and 11.2% hydrogen. We calculated this earlier. And they did the ratio of those percentages, 7.93. Then we look at the percentages in the H2O2 and look at that ratio, 15.84. Divide those two percentage ratios and you'll get a whole number. Okay? So the ratio between the two compounds will be a whole number as long as they're made of the same element.